And welcome back. We're going to be looking at the radioactive decay law. And in order to do that, we're going to have to use some of our new math skills that we've been learning in calculus, or Math E. So let's take a look at this first little graph I already have here. Here on the left side there, that is the amount of radioactive substance that you have. And here where it says N naught, that is the amount you start with, however much it is, whether it's 10 grams or a kilo. It doesn't matter. It's what you start with. And this here is the timeline. The timeline, it can be in hours, days, seconds. That depends on what you're dealing with. Some things have such a short half-life that it doesn't make sense to do anything other than seconds. But again, that just depends on what you're dealing with. So here we have 0.5 NO, or N naught. That is when we have half of what we started with. And correlated to that is the half-life. So when you have the time that has gone by that is equivalent to the half-life, then half of what you started with is gone, or has decayed into something else. Saying it's gone is probably the wrong word. This one we'll come back to in a little while. It's rather interesting, and it's connected to the decay constant and the inverse of it, but that'll make sense later at the very end of this. Well, we have to start somewhere, so let's get into the first little relationships that we can describe. This one here, the change in the amount of substance that you have, in other words, as things start to go down this and decay, is related naturally to the change in time. As time goes by, the stuff is breaking down. This, of course, that is the decay constant, and then there's a negative in front of it. And then you just rearrange it into this one here on the right. Now, once you have that, we can take the next step. I bet some of you are already guessing, we're dealing with differential equations, so we'll have to have a little fun here. All right. Since we put it into this form, we can then easily integrate both sides. We're going to integrate this end of that at the same time. So we'll go ahead and do that. And that's what this is right here. And we're going from the amount of substance that we start with, and then the amount that we have when we're done. Okay. Now for some of you, this will be rather straightforward, and you'll understand how this is treated. This is also the beginning of the time, and then the time to which we are integrating. So let's go ahead and get the next step there, and I'll bet some of you will see it instantly. The others of you who don't, go ahead and pause the film and open up your textbooks and see if you can find why this makes sense after the integration. For those of you who do get it, well, we'll just take the next step now. Okay. Now this here that I put in a kind of a amber color, that is the well recognizable formula for radioactive decay, meaning you will have, as this says, you will have a certain amount after a certain amount of time. So you start with, whatever it is, maybe a kilo or something. And then after a certain amount of time, you have a certain amount that has not yet decayed. This is just the time, whether it be in seconds or hours or days or whatever. And then the decay constant. It really is a nice, straightforward little formula there. Now we're going to need to look a little further, because as you can see, I have put in the amount when we have half of what we started with, including the time in half. So let's take a look at this next part here. Here we can see that, okay, we want to analyze this graph And we want to see what happens when the formula is changed into our specific conditions. In other words, when the amount we have left is half. We still started with the amount we started with. That's pretty self-evident. This part here doesn't change. But the t is now this t, the one that we put down there. So let's trade all those things out. Let me clean it up a bit. All right. Now what happens when we do that? I've gone ahead and cleaned up a few things. I needed some room, so I took away the white there. Okay. Here you can see that you have the n naught on each side. So that can just be divided out. And when we do that, we end up with a nice clean next part here. You can see that if it's on both sides, it just divides away. And so only the 0.5 is left. Now, you remember maybe that when you have an exponent and it's negative, you can also write that as 1 divided by the positive exponent on the bottom. If you don't remember that, just go back to the rules of exponents. I'm limited to 10 minutes on these things, so I can't explain too much. All right. Now that can easily be, after the inversion, analyzed. I bet some of you are already saying, oh, I know what to do with that. Since e is the base for the natural logarithm, if we take the logarithm of this and that, both sides, at the same time, then we end up with something that is pretty easy to handle. I just need to change pages here. There we go. Now, ln2, I want to keep it this way. I like the exact number better than the approximation of 0.69, so I'm going to leave it that way. Now, I've turned the lambda green because down here we have the inverse of lambda, and it's going to be related to this point over here. This is still the time that we are analyzing. We're looking for this particular instance. And you might see that, wow, this is really a kind of interesting situation. At a particular time, in other words, the half-life, when you get to the half-life, you have this relationship. You have the ln of 2 times this, which is the same as just ln2 divided by lambda. I found that rather interesting the first time I saw that. And it turns out that in some textbooks, they will call the inverse of lambda tau. If that's the case, if that's what your textbook has, that's fine. It doesn't matter. It's just different ways of doing the same thing. And in that case, you might see something like this. You would see tau times ln2. Some texts would just estimate it like this, and then they would continue with the number of decimal places that they wanted. Otherwise, it could be tau times ln2 instead of the approximation. So I hope that helps with understanding what the laws of decay are and how it works. Now that you have this formula and this, you should be able to do some really fun things. Like in another example, you may have a certain amount of substance and you say, we have a certain rate of decay. That rate of decay has decreased by, say, 20%. You should be able to now calculate the half-life of that just based on the information given. So we'll be doing that in part 2. Thanks for listening.